right, good evening, everybody, and welcome to our fourth and final live session of the mod. It's hard to believe that the month is already over, but here we are, week 4. Our topic this week is deductive and inductive reasoning, and this is a topic that can be really difficult to wrap your head around. I know that as you work through the course material this week, sometimes it's hard to keep things straight, so I really want to focus in this week's live session on getting a good grasp of the difference between deductive and inductive reasoning, because that should set you up nicely to complete your assignments for this week. I do want to remind you, though, that because this is week 4, there is no late work after Sunday. Remember, I have waived all late penalties for this class, so as long as you get your work in before the end of the mod, which is 11:59 p.m. Mountain Time on Sunday, as long as you get your work in before that, there will be no late penalty. So make sure that you're working on that. Sunday is the absolute deadline for this course, so get to work on it now if you aren't already. If you have missing work, now is the time. I also want to remind you, I wish I didn't have to revisit this, but in my experience, sometimes it's good to have a little reminder of this. All work that you submit for this course must be your own work. I know as we get to the end of the class here, and maybe you're taking another class at the same time, maybe you've fallen a little bit behind. I know it can be tempting to copy and paste from the internet in the hopes that you won't get caught plagiarizing. I'm telling you now, it's not worth the risk. Everything you turn in gets run through a plagiarism checker. On top of that, I've been teaching this class for quite a while now, and I've gotten pretty good at spotting what is and what is not original student work. So make sure that all work that you submit is your own work. If you are using an internet source, which you're certainly allowed to, you're certainly encouraged to, in fact, on many of the assignments, just make sure that you're using those citations and references to give credit where credit is due, because all work that you submit must be your own work. If you quote or paraphrase from another source, make sure that you give proper credit. Okay, now that that's out of the way, I want you to think about this for a little bit. What is going to happen at roughly 6:30 a.m. tomorrow? What is going to happen at roughly 6:30 a.m. tomorrow? Time zone shouldn't matter too much. It'll be roughly speaking 6:30 a.m. local time, give or take a little bit. What is going to happen at roughly 6:30 a.m. tomorrow? Give you a little clue, it also happened at roughly 6:30 a.m. today. You don't have to answer now. I just want you to think about that. Have that bouncing around in the back of your mind. Oh, you do have to answer now. I forgot the order of my slides. It's sunrise, right? The sun will come up tomorrow, roughly 6:30 a.m., give or take a little bit there. Sun came up at roughly 6:30 a.m. today. The sun will come up. How do we know? How do we know that the sun will come up tomorrow morning? And here is the point, by the way, where there's always some smart aleck who says, well, the sun doesn't actually come up, the earth rotates, so the sun stays still. Granted, okay. How do we know that the sun will appear to come up tomorrow? How do we know? Now, this is the point at which you don't have to answer right now. Just ponder this for a little bit. How do we know that the sun will come up tomorrow? Now, I want you to set that one aside and take a look at this for me. 1, 2, 3, 4. 1, 2, 3, 4. What comes next? 1, 2, 3, 4. What comes next? This is obvious, right? 1, 2, 3, 4, 9. Clearly. Some of you are like, come again? All right, where did that 9 come from? What went wrong here? If you thought 5 was next, if you heard 1, 2, 3, 4, and 5 is what you thought was next, what went wrong? Where did that 9 come from? Think about that for me. What went wrong here? Why is it a 9 and not a 5? We're going to circle back and revisit that a little later in the lecture. But for now, we're going to watch a quick clip here. This is an example of some less than stellar reasoning. If technology will cooperate with me here. Come on, computer, don't let me down.
Could be any one of them, but which one? Which ones?
Pretty fishy what happened to me on that ladder.
You mean where there's a fish, there could be a penguin?
But wait, it happened at sea. See? See for Catwoman.
Yet, that exploding shark was pulling my leg.
The Joker.
It all adds up to a sinister riddle. Riddler. Riddler?
Oh, thought strikes me. So dreadful I scarcely dare give it utterance.
The four of them. Their forces combined.
Holy nightmare.
Batman, could it be?
I don't know. But I think I know where to find a clue. Come on, Robin. To the Batcave. We haven't one moment to lose.
Okay, so that's a clip from the old Batman TV series from the 60s. And you can see this is not exactly good logic. My favorite is, it happened at sea. C for Catwoman. Obviously, the letter C is different from the word see, S-E-A. Now, sometimes in the real world, we encounter arguments that are obviously flawed, right? So in this case, we have an argument where anybody watching this clip could see that there's some faulty logic going on. Sometimes we encounter arguments and we know that there's something wrong with them, and we can put our finger right on the problem. However, there are many times in our lives where we encounter arguments that we know kind of instinctively are flawed. We know there's something wrong with them, but when we try to articulate what that is, what exactly the flaw is, we can't quite do it. We can't quite put our finger on what is wrong with the argument. A lot of times that comes from mixing up deductive reasoning and inductive reasoning. So today we're going to walk through the differences between deductive reasoning and inductive reasoning, and hopefully this will equip us to deal with those arguments where we know that there's something wrong, but we can't quite pinpoint what exactly it is. So deduction versus induction. We also call these deductive reasoning versus inductive reasoning. So deduction and deductive reasoning are the same thing. Induction and inductive reasoning are the same thing. Now, as the course material for this week has explained, deduction and induction are our two main ways of reasoning towards a conclusion. So these are two different approaches to logic, deductive logic and inductive logic. They're two different ways that we reason towards a conclusion. They're two different techniques, I guess you could say, that we use to reason towards a conclusion. And it's really important to understand the differences between the two. To do that, we're going to start with deduction. We're going to walk through deduction. Deduction starts with a general principle, and it reasons to what we call a necessary conclusion. There's a few things we need to break down here. First off, this general principle. What do we mean by that? Essentially what that is it's a principle or a claim or a quality that applies to all members of a general group. And so it's a claim that applies to all members of some general group. Now, then it reasons to a necessary conclusion. What does that word necessary mean? I want you to think about just everyday language. What do we mean when we say something is necessary? What do we mean by the word necessary, just in general usage? We mean that it's something we need to do or we have to do, right? It is necessary for me to give a 1-hour live session each week. That means I have to do this, right? It's part of my job. It is necessary for you to turn in your work in order to get credit for this class. Does not mean it's optional, right? It means you have to do it. So in everyday usage, necessary is something that we have to do or we need to do. In logic, necessary has a slightly different meaning, but it's similar to that. There's a connection there. In logic, a conclusion is necessary if the premises are true and the conclusion must also be true. In other words, a necessary conclusion cannot be false if the premises are true. So deduction reasons to a necessary conclusion. This is a conclusion that must be true if the premises are true. The conclusion cannot be false if the premises are true. Now that if is going to prove to be absolutely crucial. That if is going to be very, very important. For now, all you need to know is that a necessary conclusion is one that has to be true. So we get that has to sense of necessary. The conclusion has to be true if the premises are true. That's what we mean by a necessary conclusion. So here's an example of a basic deductive argument. Premise 1, all mammals have hair. Now you'll notice this is a general claim. It ascribes a claim to all members of some general group. In this case, all mammals, right? All members of the group mammal have this general claim, hair, right? All mammals have hair. Premise 2, whales are mammals. And then the conclusion, therefore, whales have hair. All mammals have hair, whales are mammals, therefore whales have hair. So let's look at a few things. First off, general claim, right? All mammals have hair. All, not just some of them, all of them. That is crucial because that all tells us that any subgroup or any individual that falls under this broader group mammal will have this quality here, right? So what happens is we take this all mammals have hair. Premise 2 tells us whales are mammals. Because this says all mammals have hair, we know we can substitute whales in the place of all mammals. And that gives us whales have hair. Lo and behold, that is our conclusion. Whales have hair. Right? So the general claim is key here. Now, let's see if this is a necessary conclusion. Is it possible for the conclusion to be false if the premises are true? How do we answer that? Well, you might think we need to research and determine if the premises are true, right? Here's the thing though, when we encounter arguments, we're not always going to know if the premises are or are not true. Sometimes only an absolute expert in some particular field would be able to determine that, and we may not always have access to that sort of information. So to test the logic of an argument, we don't have to know for sure if the premises are true or not because of that if, right? A necessary conclusion is one in which if the premises are true, the conclusion must also be true. This if tells us we can play a hypothetical game. So say we don't know, these premises happen to be true, by the way, and the conclusion is also true, but say we didn't know that, right? Say we have no idea whether all mammals have hair. We have no idea whether whales are mammals. That if, in the definition of a necessary conclusion, tells us we can set aside the question of whether the premises are actually true, and we can set up a hypothetical. We can say, if these premises were true, what would that tell us about the conclusion? In other words, hypothetically, let's assume that the premises are true. So if it is true that all mammals have hair, and if it is true that whales are mammals, then we have to conclude that whales have hair. Right? If these two things are true, the conclusion cannot be false. Now notice, it does not matter if these are actually true. We're talking a hypothetical situation. All we're testing is the validity of this argument. Validity, not truth. Because deductive arguments can be true or false, but they can also be valid or invalid. An invalid argument is one in which the conclusion does not necessarily follow from the premises. So a deductive argument is invalid when the conclusion is not necessary. The conclusion could be false even if the premises are true. So truth and validity are two separate questions. To illustrate this, let's look at another example here. Premise 1, any person would be rich if they owned Microsoft. Now notice it's a general claim, right? Any person who owned Microsoft would be rich. Any individual who falls under the group owning Microsoft would be rich. That's the general claim here. Premise 2, I, Taylor Norwood, do not own Microsoft. I know this is shocking given my incredible technological skills, but I don't own Microsoft. I wish that I owned Microsoft, but I don't. Conclusion, therefore, I am not rich. Now, every single part of this argument is true. It is true that any person would be rich if they own Microsoft. Just ask Bill Gates or the family of the late Paul Allen, the co-founder of Microsoft. Yeah, you'd be doing all right if you own Microsoft. Premise 2, I do not own Microsoft. This is, in fact, very, very true. I do not own Microsoft. The conclusion is also true. I am not rich. Not by any stretch of the imagination am I rich. Believe it or not, we adjunct instructors of philosophy are not just rolling in the dough. So every part of this argument is true. Does that make it a good argument? The answer is no, because truth is not the only question. There's also the question of validity. Remember, a deductive argument is valid if the conclusion is necessary, meaning the conclusion cannot be false if the premises are true. Now, we know the premises are true here, right? We've already established that. Any person would be rich if they own Microsoft. I do not own Microsoft. The question then is it possible for the conclusion to be false even though these premises are true? So could I possibly be rich even though I don't own Microsoft? And the answer is yes, right? Because there are lots of ways that a person could be rich. Maybe I don't own Microsoft, but I own Apple. So I'm even better off. Or I own Amazon. Or maybe I don't own any tech company, but I own stock in some other big company. Or maybe I don't own any stock at all, but I inherited a whole bunch of money from a rich relative. Or I own a bunch of real estate and have a lot of tenants who pay me rent each month. None of those are true, but they could be, right? It is possible for me to be rich even if these premises are true, which tells us that this conclusion is not a necessary conclusion. It is possible for this conclusion to be false, even though the premises are true. This tells us that we have an invalid argument. It's true, every single part of it is true, and yet it is invalid. So from a logical standpoint, this is a bad argument. This is something that trips people up sometimes, right? Sometimes we think if an argument is true, it's a good argument. That is not always the case. You've probably heard the expression, even a blind squirrel finds a nut, right? Even a highly illogical thinker may come up with an argument that is true in each part of it, but that doesn't make it a good logical argument. So an invalid argument could contain only premises that are true and a conclusion that is true, but it still isn't logically valid, right? We want, in order for an argument to be a good argument from a logical standpoint, we would want it to be true and logically valid. Now, the flip side of this is also true. An argument can be valid and not true, right? So just because an argument is valid does not make it true. Give you an example of this. Premise 1, all four-legged creatures have wings. Premise 2, all spiders have 4 legs. Conclusion, therefore, all spiders have wings. Now, every part of this argument is false. All four-legged creatures do not have wings. How do I know? Well, all I have to do is look down at my dog, Jade, who is sleeping in the floor. She has 4 legs, 0 wings. So, that right there demonstrates to me all four-legged creatures do not have wings. Premise 2 is also false. All spiders do not have 4 legs. All spiders have 8 legs by definition. So that is also false. The conclusion, all spiders have wings, is also false. So far as I know, no spiders have wings. So those of you who are afraid of spiders out there, you'll be glad that they're not a flying threat, right? So every part of this argument is false. So it's a bad argument, right? It's logically unsound. No, actually, it's good. It's a good deduction. Yeah, it's actually a valid argument. Why? Well, because the conclusion necessarily follows from the premises. In other words, the conclusion has to be true if the premises are true. So again, we set aside the question of the actual truth and we play the hypothetical scenario. If it were true that all four-legged creatures have wings, and if it were true that all spiders have four legs, then we could take all spiders and plug it in the place of all four-legged creatures. And that would give us all spiders have wings. Lo and behold, that's our conclusion. So the premises lead necessarily to the conclusion. So this, as Watson here from Sherlock Holmes tells us, is a good deduction. So it is a valid argument. Now, we can only test the validity of deductive arguments with logic. So the role of logic is to test the validity. In other words, the role of logic is to test the relationship between premises and conclusion. Does the conclusion necessarily follow from the premises? If so, it is a valid argument. If not, it is invalid. In order to test the truth of an argument, we need observation and/or data. We call that empirical evidence, by the way, evidence that's based on direct observation or data. So how do I know that all four-legged creatures do not have wings? Well, observation, right? I look down, I see a four-legged creature with 0 wings. So truth is tested by observation and data. Validity is tested with logic. So that's deduction in a nutshell. I want you to think now about the role of deduction in your own everyday life. Do you rely on this sort of reasoning in your own life? Where you start with general principles or general rules and then reason to a necessary conclusion. Spoiler alert, everybody uses deduction some. Everybody uses deduction some. If you have a career field that uses a set of rules, okay, those are general principles. You generally use those principles and apply them in specific situations, and that gives you a necessary conclusion. You use deduction to arrive at the proper conclusion. I got ahead of myself a little bit. Next question is, do you rely on deduction in your career field? And again, the answer here is going to be yes. Everybody uses deduction some. The question is, how much? Right? Some career fields use deduction more than others. So scientific career fields, for example, tend to rely pretty heavily on deduction. But even graphic design, I know many of you are graphic design majors. Graphic design uses deduction, right? Just think about principles of graphic design. Say you have these principles which give you basically a set of general guidelines. So maybe one of these guidelines is don't use a light colored font on a light background. Maybe that's a general principle, right? Or a general rule. So premise one, all light backgrounds should use dark fonts. Premise two, this particular project has a light background. Therefore, I should use a dark font. And that's using deduction, starting with a general principle and applying it to a specific project to give you a necessary conclusion. That's just one example of how you might use deduction. Your task is to think about how much you use it. What is the role of deduction in your everyday life and in your career field? Now that we have a pretty good idea of deduction, let's shift gears and talk about induction. Right? This is the other side of the coin, the reverse of the medal. Induction starts with observation and then reasons to a general principle. So whereas deduction starts with a general principle and then it reasons towards a conclusion that we can test with observation, induction kind of goes the opposite direction. We use observation as our starting point, and then this helps us develop a general principle, or a general pattern would be a better way of expressing this, I guess. Induction is concerned with probability rather than necessity, and this difference is crucial. Whereas deduction aims at a necessary conclusion, a conclusion that has to be true, right? A definite conclusion. Induction, on the other hand, only aims at a probable conclusion, a conclusion that is more likely true than not. So let's look at an example to illustrate what I mean here. Premise one, most professors are old. Premise one, most professors are old. For the sake of this argument, we'll say old is 65 or older. If you happen to be 65 or older, do not take this personally. That is an arbitrary number that I picked just for the sake of this argument. You're only as old as you feel. And I'm only partly joking there because I know people who are much older than 65 who seem much younger, and I know people who are much younger than 65 who seem much older. So I do think it's kind of relative. But for the sake of this argument, we'll say old refers to anybody over the age of 65. So premise one, most professors are old. How would I know that? Well, either I have determined this through my own observation. So by now, through my bachelor's degree and my master's, and I'm done with coursework on my PhD, I'm just working on my dissertation. In all that time, I've had dozens of professors. So maybe I look back on my dozens of professors and I say, you know what, 90% of my professors were over the age of 65. So maybe I base this premise on my own observation. Or maybe I read an article that says 80% of university professors are over the age of 65. So it's somebody else's data. Either way, it starts with observation or data. Okay, so most professors are old. Premise two, Taylor Norwood is a professor, yours truly. Therefore, Taylor Norwood is probably old. This is an inductive argument. Starts with observation, and then it leads to a conclusion that is actually a general claim in disguise. Now, it looks like it's a specific claim, right? Taylor Norwood is probably old. What this is saying is that if most professors are old, then any individual who is a member of that group is probably old, is more likely than not to be old. So it's a rephrasing of that original premise, only here we've isolated a particular member of that group. So it's a claim that applies generally. We just happen to be talking about one specific member here. So Taylor Norwood is probably old. Now, I am not over the age of 65. In fact, in just a couple weeks, I'll be 34. So I'm a long way from 65. Not old by any stretch of the imagination. So, does that mean this is a bad argument or this is a false argument? No, it's a good argument. And the conclusion is not false. It's true. Right? Taylor Norwood is probably old. Any person who is a member of the group professor is probably old, according to this argument. Probably just means more likely than not. What it's saying is that based on my observation or based on my data, any member of the group professor is more likely than not to be old. So Taylor Norwood is a member of that group professor, which means, based on my observation, based on the pattern I've identified, it is more likely than not true that Taylor Norwood would be old. Now, as it happens, Taylor Norwood is not actually old, but the odds, based on my observation, still hold that any member of that group professor is more likely than not to be old. So even though I'm not old, the conclusion is true because it's this probably here, right? If you took out the probably, if it just said Taylor Norwood is old, then you have a flawed argument, right? Because A, I'm not old, so it's untrue, and B, it's invalid because the conclusion would be claiming more certainty than the premises warrant. If this said all professors are old, then we could conclude that Taylor Norwood is old. But as long as it says most, the best we can conclude is that Taylor Norwood is probably old. Let's look at another example here. Premise one, I have seen the sunrise every day of my life. I guess I have not seen the sunrise every day of my life. I've seen a lot of them, thanks to duck hunting. You got to get up pretty early. So maybe this would be better if it said, I have seen that the sun has risen every day of my life. Premise two, my life will probably continue tomorrow. How do I know? Well, I'm relatively young. I'm about to be 34. I'm in pretty good shape. I'm pretty good health. In my experience, people who are relatively young and in pretty good shape and in pretty good health tend to continue to live for a little while. The conclusion then, I will probably see the sunrise tomorrow. This is the answer to that question. How do we know the sun will come up tomorrow? How do we as individuals know? Now, sure, you could refer to textbooks on physics and astronomy and everything, but it all boils down to the same thing. It boils down to observation, right? Based on our observation of the past, we are trying to predict future outcomes. Now, my observation of the past has told me that the sun rises every day. Okay, my observation also tells me my life will probably continue tomorrow. You put those together, and that tells me I will probably see the sunrise tomorrow. Is this a good argument? The answer is yes, this is a good argument. This is a valid argument. If we take out the probably, though, if we say I will see the sunrise tomorrow, then we're in trouble, right? So when I asked you what's going to happen at roughly 6:30 a.m. tomorrow, if you said the sun will come up, then you've committed a flawed argument, right? You've made a mistake. You've committed an invalid inductive argument. If you say the sun will come up tomorrow, you're claiming certainty, when the best we can do is claim probability. Because here's the crucial thing with induction: past experience cannot guarantee future outcomes. Past experience cannot guarantee future outcomes. What we do with induction is we take all of our observation, all of our experience, and we identify a pattern. And we use that pattern to predict future outcomes. But the problem with predicting future outcomes is they're always uncertain, right? That's why we can only ever claim probability. To do more than that would be to claim more certainty than our experience warrants. So just because I've seen the sun rise every day of my life and that my life will probably continue tomorrow does not guarantee the future outcome that I will see the sunrise tomorrow, right? Maybe a satellite falls from the sky and crushes me, so my life doesn't wind up continuing tomorrow. Maybe an asteroid smashes into the Earth, Armageddon style, and the Earth stops rotating on its axis and the sun doesn't come up tomorrow. Right? Just because it's happened every day so far does not mean it will definitely continue to happen every day from here on out. Past experience does not guarantee future outcomes. We call that the problem of induction, right? The problem of induction. What we mean by that is the best induction can give us is a probable prediction of future events. Here's another example. This example, for some reason, is in every logic textbook since the dawn of logic, basically. So I kind of have to include it here. Premise one, I have observed thousands of ravens. Maybe I'm an ornithologist, right? Maybe studying birds is my occupation. So I have observed thousands of ravens. Every raven I have seen is black. So we start with observation. We identify a pattern. I have observed thousands of ravens. Premise two, every raven I have seen is black. And then we generate a prediction about the future. Therefore, all ravens are probably black. What I'm saying here is that I'm predicting that every raven I encounter in the future will also be black. All ravens are probably black. Now, this is a valid inductive argument, right? If I said all ravens are black, then it's invalid because I'm claiming more certainty than my premises warrant. All I know for sure is that all ravens I have observed in the past are black. Now, this tells me that the ones I observe in the future will probably be black, but there is no guarantee there, right? The problem of induction means that all it takes is one counterexample to shoot down this claim, right? So if I say all ravens are black, all it takes is one albino raven, which I don't know for sure if those exist. I'm guessing that they do, which would mean that all ravens are not actually black, and therefore it would be an invalid argument, right? As long as we say all ravens are probably black, though, then we have a valid inductive claim. So inductive arguments can also be valid or invalid. They become invalid when they assert certainty rather than probability, when you overstep what your premises support. So 1, 2, 3, 4, what comes next? If you said 5 probably comes next, you've made a valid inductive claim. Essentially what you've done And this is subconscious. Most induction that we do day to day happens on a subconscious level. So what happens in your brain when you see 1, 2, 3, 4, and I say what comes next? Your brain says very, very quickly and very subconsciously, it says, in my experience, the numbers 1, 2, 3, 4 are usually followed by 5. That's premise 1. Premise 2, here I see the numbers 1, 2, 3, 4. Conclusion, therefore, 5 is probably next. Now, if you say 5 probably comes next, you've made a valid claim. Right? You've identified a pattern, you're predicting a future outcome. Even if you're wrong, you've only claimed probability. Now, if you saw 1, 2, 3, 4 and you said 5 is next, then you've made an invalid claim because past experience does not guarantee future outcome. Where did the 9 come from? Right? I have had students go nuts over this. Right? They try to come up with all sorts of explanations. Oh, well, 1 plus 2 equals 3, 2 plus 3 is 5, plus 4 equals 9. It's nothing as complicated as that. I literally just picked a number other than 5. Okay? Just so that if you guess 5, you would be wrong. To illustrate the point that past experience does not guarantee future outcomes. So the best we can hope for is a claim of probability when we rely on induction. Now think about this. Do you rely on induction in your everyday life? The answer to this one is definitely yes. We all use induction far more than we probably realize. Anytime we identify a pattern and use it to predict what is going to happen, we're using induction. That's what we're doing, right? And we're programmed to do this. We're programmed to look at our experience, isolate patterns, and use that to predict what's going to happen next. That's why if you've ever been driving and you see somebody with their turn signal on, like they're going to change lanes or they're going to turn, and they never do, they just keep driving with their turn signal on. I don't know about you, that drives me nuts. Turn your signal off. What are you doing? The reason that is so irritating is it frustrates our predictions of what is supposed to happen, right? Our experience shows us that when someone has their turn signal on, it means they're either going to change lanes or turn. Therefore, when we see a car driving with their turn signal on, we think, oh, they're about to change lanes or turn. When they don't, we get irritated because our prediction is wrong, right? That's an example of induction in everyday life. Okay? We use induction all the time. Anytime you identify a pattern and try to predict future outcomes, you're using induction. An example of this, I know many of you have kids, so you can relate to this, right? Kids settle into routines really, really easily. And as a result, we parents tend to settle into routines too. So in my house, my oldest daughter, who will be 6 in 2 months, she gets up at about 10 till 7 every morning. That's her routine. She gets up at 10 till 7. My other daughter, who will be 4 in about 2 months, she likes to sleep in a little bit more, so she's usually up closer to 7:20 or 7:30. She usually sleeps in about half an hour later than her sister. Now notice I'm saying usually here, right? Induction tells me that because my past experience shows that my oldest daughter usually gets up at 10 till 7, I can predict that she will probably get up at 10 till 7 tomorrow. Now I can predict that, but as any of you with kids know, kids are good at thwarting our predictions, right? So tomorrow might be the fluke where she gets up at 6 o'clock instead of 6:50. Or maybe she sleeps in tomorrow till 7:30 and my other daughter gets up early, right? Just because there's a pattern doesn't mean the pattern holds always, right? So we use induction to predict outcomes, right? I use it to predict what time I expect my daughters to get up tomorrow, but that doesn't mean that they actually will. Right? The other thing I want to point out about induction in your everyday life is we tend to build kind of networks of inductive arguments. So that argument about how I know I will see the sun rise tomorrow, premise 2 is my life will probably continue tomorrow. How do I get that premise? Well, I said I'm relatively young, I'm in relatively good health. In my experience, people who are relatively young and in relatively good health tend to continue to exist for a while. That is its own inductive argument. And then I take the conclusion of that argument and I plug it in as the premise in another argument. So what we do is we create these kind of webs of predicted outcomes, right? What we expect to happen. These kind of chains of inductive reasoning. That's what we do routinely. We're just programmed to identify patterns and make predictions as a result of them. And we weave them all together, and when one prediction goes wrong, that can throw off multiple other inductive claims. So, do you rely on induction in your career field? Again, the answer here is going to be yes. The question is how much, right? All career fields have some reliance on observation and experience, right? And you use that to predict what is going to happen in other situations so that you know how to handle them, right? Everybody uses induction some. The question is, how much do you use it in your career field? And I can't really answer that for you. You've got to think about that one for yourself. So, deduction and induction. These two are closely related because induction often provides us with the general principles on which we rely when we use deductive arguments. So they go hand in hand. They're two sides of the same coin here. To illustrate what I mean, I want to use this graph or this chart here. See, induction starts with observation, right? I have observed thousands of ravens. Then we identify a pattern. Every raven I have observed is black. Then we generate a hypothesis. Therefore, all ravens are probably black. It's a hypothesis because of that probably, right? That's saying that we don't know for sure, right? There's not certainty there. Now, when a hypothesis has stood for quite a while, has been tested repeatedly, and has not yet been disproved, then to test it further, we elevate it to the level of theory. Right, so when we say, when we talk about like scientific theories, we don't mean that's just a guess, right? We don't mean that this is just an idea, a theory that somebody came up with. What we mean is that this is a hypothesis that has been repeatedly tested and so far has not been disproven. So we elevate it to the level of a theory. We take out the probably, and that gives us a definite general claim, right? So instead of all ravens are probably black, that gives us all ravens are black, right? That's the theory. Then we take that theory, that general claim, and we plug it into a deductive argument. And we use that, then we use deduction to generate new hypotheses, which we test with observation and confirmation. So to give you an example of this, say I have observed countless species of mammals. And I have identified a pattern that every mammal I have observed has some sort of hair. Therefore, all mammals probably have hair. That's my hypothesis. Then I elevate it to the level of a theory. I take out the probable. All mammals have hair. That gives me the starting point for the deductive argument. All mammals have hair. I generate a new hypothesis. Whales are mammals. Therefore, all whales have hair. How do I test that? Observation, right? I go out and I study whales, and that either confirms or disconfirms the theory, right? So induction and deduction go hand in hand. Now, our goal in this course is to improve our critical thinking and our logical skills, right? How does this help us? How does recognizing the different types of reasoning help us achieve the goal of improving our critical thinking and logical skills? Just think about that for a second. How does this help? Okay. The answer is that each type of reasoning, deductive reasoning or inductive reasoning, makes different claims and it uses different methods. So it's important for us to be able to identify in an argument what sort of reasoning is being used, because that tells us the sort of conclusion that we ought to be looking for, right? If it's a deductive argument, then we should be looking for a necessary, definite conclusion. If it's an inductive argument, we should be looking for a probable conclusion, right? And each type is important, but one may be more prevalent in your career field. So it's important for you going into a career field to figure out which sort of reasoning is relied on more frequently. So you know the sort of reasoning you need to rely on more frequently. And each type of reasoning claims a different degree of certainty. Many fallacies result from claiming a degree of certainty that is not warranted by your premises. Right? Many different types of fallacies are a result of mixing up induction and deduction. Right? You have inductive premises, but a deductive conclusion, and that leads you into a fallacy. Right? Your conclusion claims more certainty than your premises can back up. That leads you into a fallacy. All right, let's talk about your discussion prompt and your assignment prompt for this week. The discussion prompt is fairly straightforward. For this discussion, bring examples or an example from your own life, personal or professional, or those you know, or conduct online research and find an example when invalid deductive arguments were used to draw a conclusion. There's a lot of ors in that sentence. What is it asking you for? All it's asking you for is an example of an invalid deductive argument. Where do you find that example? Well, it could be an example from your own life, either your personal life or your professional life. If you can't think of an example from your own life, either personal or professional, then think about other people that you know. If you can't think of an example from somebody you know, then conduct online research and find an example online. Make sure you're giving proper credit, right, if you use an online example. So these are suggestions of where to find an example. The key here is to find an example when invalid deductive arguments were used to draw a conclusion. Explain what was wrong and why. So, why is it an invalid deductive argument? So, say, for example, if there's a fallacy, explain what the fallacy is. Identify what went wrong with the argument. What makes it invalid? Explain what makes it invalid. Don't just say, this is an invalid deductive argument. Tell me why it's invalid. Tell me how you know it's invalid. Explain. That's the key here. Explain what was wrong and why. Then it says, in replies to your classmates, you should provide counterexamples to dismantle the fallacy. This is just a suggestion. If you're looking for something to do in your response posts, you can reply to your classmates and offer counterexamples to take apart the fallacy. So if they've offered a flawed argument, you can offer an example that points out something wrong with the argument. Or you can take their argument and rephrase it to make it valid, right? You could fix the argument. Those are just a few suggestions for response posts. But the key here is in your primary post, you should find an example of an invalid deductive argument and explain what was wrong and why. Explain why it is invalid and how you know that. All right, so discussion, hopefully fairly straightforward this week. The assignment this week asks as follows. For this assignment, you are being asked to clarify your understanding of the difference between deductive and inductive approaches to reasoning. That's exactly what I've been doing in this entire live session. So this entire lecture is aimed at helping you prepare for this assignment. You're being asked to clarify your understanding of the difference between deductive and inductive approaches to reasoning. Write a paper of at least 600 words where, using examples, you first explain the difference between deduction and induction. So, tell me what deduction is in your own words, and give me an example of a deductive argument. And then tell me what induction is in your own words, and give me an example of an inductive argument. Now, you are welcome to draw on this live session for your explanations of the difference between deduction and induction, but your examples need to be your own. In other words, don't use my examples from this lecture in your paper, right? I already know these examples. I want you to give me your own examples. So, explain what deduction is. Give me an example. Explain what induction is. Give me an example. Then answer these questions. In what ways can inductive reasoning be useful in your chosen field, even though it doesn't aim at certainty like deduction does? So in other words, when I asked you, do you use induction in your career field? I wasn't just asking that for fun. That's part of your prompt, right? How does your career field use inductive reasoning, even though induction only aims at probability, not certainty? So after you've answered that, then Choose 3 fallacies from among those you studied in week 3 and explain how the presence of those fallacies can affect the strength of the inductive argument you used as an example. So up here, when you give me an example of an inductive argument, what would it look like if that argument were contained 3 of the fallacies you studied from last week? Okay, so pick 3 types of fallacies. Let's say like ad hominem, hasty generalization, slippery slope. There's just 3 random ones. What would your argument of try that again. What would your example of an inductive argument look like if it committed those fallacies? How would those fallacies affect an inductive argument rather than a deductive argument? And then finally, what can be done to avoid committing these fallacies in your future work? How can you avoid committing fallacies in the future? Answer those questions and you'll be in good shape. As always, I will post an announcement in the next day or 2 breaking this down step by step in writing, just like I've done here. All right, if you have questions about anything, as always, shoot me an email, Taylor, Taylor, .norwood, Norwood, @independence.edu. That's it for tonight. Thanks very much for your attention. Thank you all so much for your hard work in this class. It's been a pleasure having all of you in class. I hope you got something useful out of it. I've certainly enjoyed my time over the past month. I hope you have too. Thanks again. I appreciate your effort. Everybody have a good night.